Hi, welcome to my topic Circuits and Networks. I am Ravikant Malla Joshila, and today we are going to deal with class 5 of single phase AC circuits. What we have seen from our previous classes is the behavior of alternating voltage when applied to passive elements, respectively resistor, inductor, and capacitor in their pure form. When they are applied across these elements, we came to a conclusion that the current is in phase with voltage when the pure resistance is applied across alternating voltage. The conclusion what we made about inductor in its pure form that current lags voltage by 90 degrees, whereas in the case of capacitor current leads voltage by 90 degrees. In the waveform we have seen that the current is lagging voltage in the case of inductor, whereas in capacitor, the current is leading voltage by 90 degrees. In this class, we are going to see when alternating voltage applied to series RL circuit, the series RL circuit, the voltage V is equal to Vm sin omega t. When applied across this series element, the current when it passes through these two elements at one stage, it will develop a voltage VR and VL. So we can conclude that the applied voltage is equal to VR plus VL according to Kirchhoff's voltage law. What is VR? VR is R into I, and what is VL? VL is J XLI. Now in this two elements, the same current is flowing. Therefore, I'm going to remove this current and I'm going to divide by this voltage. Thereby, V by I is equal to R plus J XL, which is equal to impedance of this particular circuit. So it is clear that the voltage across resistance is in phase with current, whereas the voltage across inductor leads current by 90 degrees. So what is this then? Z. Z is known as impedance of the network. In polar form, Z is equal to Z at an angle phi. We have to determine what is the magnitude of Z and what is phi. Z is equal to under root of R square plus XL square, where you can rewrite this XL as omega L. So XL square becomes omega square L square. So this becomes the magnitude of the impedance. And to find out the angle phi is equal to tan inverse the imaginary component by real component, that is XL by R. So this is how we estimate the impedance of series RL circuit. Now we know that voltage and current, when they are said to be in phase, the phasor diagram represents like this. When it is a resistive network, the same phasor diagram resembles like this, means the voltage across resistance is said to be in phase with current under pure resistance, whereas when you see the voltage and current relations of inductor, the voltage and current, they are quite opposite to one another at an angle of 90 degrees. That is, the current through inductor lags voltage by 90 degrees, or voltage through inductor leads current by 90 degrees. So when we are going to take the combination of all these phasors, we know that resistance voltage and current are in phase, whereas the inductive voltage is leading current by 90 degrees. Now with these two phasors, I'm going to get the total voltage V is equal to VR plus VL. Therefore, I can treat the angle between them as phi. So with this, I'm going to obtain the voltage triangle in this form. You have VR, VL, and V is equal to VR plus VL. If this is true, I can even construct the phasor diagram for resistive and inductive reactive with impedance at an angle phi. So this becomes the impedance triangle of RL circuit. when you're going to take the trigonometry relations, you're going to get cos phi is equal to r by z. So this is how you represent the phasor relationship for RL circuit. Now we know that the current is lagging voltage for RL circuit. Now if at all you calculate the power, power is equal to V into I. So we are substituting the value of V, we are substituting the value of I. So I is here, Im sine omega t minus phi. So when I'm going to take Vm Im on the left side, sine omega t minus phi, this has a relation of sine A sine B. So we have to go with the trigonometry formula of sine A sine B. Sin A sin B is equal to 1 by 2 cos A minus B minus cos A plus B. So we are going to apply, instead of A as omega t, instead of B we are going to apply omega t minus phi. So I'm going to substitute these values and I'm going to get the value of P is equal to Vm Im of cos phi minus cos 2 omega t minus phi whole divided by 2. So with this, I'm going to get the constant component as Vm Im cos phi by 2 and a fluctuating component which is minus Vm Im by 2 cos 2 omega t minus phi. So what does this fluctuating component indicates? The frequency of the fluctuating part is twice the applied voltage frequency, and if at all you take this average value, you're going to get the average value of this fluctuating part is equal to 0. With this, I'm going to obtain only the constant part as the average part. So average power is equal to Vm Im by 2 cos phi. You can rewrite this Vm Im by 2 as Vm by root 2 Im by root 2 cos phi, which is equal to Vi cos phi. Now here V and I becomes the RMS values. So we know that average value of power is equal to Vi cos phi. So this power is known as the average power, or it is also denoted as active power, and this power is depend upon in phase component of the current. Then what does the reactive power indicates? The reactive power is denoted by Q. So you have cos phi which is acting for active power. So to denominate reactive power, you're going to get Q is equal to Vi sin phi. From the impedance triangle, you can determine the value of the reactive power. Now, once we obtain the active power and the reactive power, we can construct a power triangle. We know that cos phi is equal to R by Z. And according to standard form of Ohm's law for AC network, V is equal to Zi. Therefore, power which we have estimated as average, which is equal to Vi cos phi, substituting the value of V, substituting the value of cos phi. So V equal to Zi and cos phi is equal to R by Z. So with this, I'm going to get the value of power, which is known as the active power, as I square R. Similarly, we can also obtain the reactive power, which is equal to I square XL. So once we obtain the active power, reactive power, we can construct the power triangle like this, which is a combination of P and Q as apparent power. S represents the apparent power. So S is equal to Vi, which is equal to I square Z. Now we can easily obtain the power factor, which is equal to cos phi, which is equal to R by Z from impedance triangle, which is also equal to VR by V from voltage triangle, and P by S from power triangle. So this is how we estimate the power calculations and power factor calculations for series RL circuit applied to AC input. Now let us go with the next circuit, that is RC circuit in series combination with alternating voltage. So we know that V is equal to Vm sin omega t, and when the current passes through this particular closed circuit, we have V is equal to VR plus VC. Now we know that VR is equal to R into I and VC is equal to minus J XC I. Now XC represents the reactive capacitance of the network. When you take the current on one side, we are going to get the impedance of the network. Now it is clear from this RC circuit that voltage across resistor is in phase with current, like in the case of RL circuit, whereas voltage across inductor lags current by 90 degrees, unlike the previous circuit. With this, I can obtain the impedance of the network, which is equal to the magnitude component as well as the angle component. So Z is equal to under root of R square plus Xc square. Now since it is minus, it becomes R square plus 1 by omega square plus, sorry, omega square C square. Now this minus sign, it has changed to like this. Now you can get the value of phi, which is equal to tan inverse Xc by R, but Xc is equal to 1 by omega C. So phi is equal to tan inverse 1 by omega RC. Now this is how the RC network is different from RL network. Now you calculate the phasor representation. We know that resistance is in phase with current, whereas voltage lags current by 90 degrees, or you can say current in capacitor leads voltage by 90 degrees. With this, I'm going to get the voltage triangle with an angle phi in this way. Once the voltage triangle is obtained, you can easily obtain the impedance triangle. And from the previous conclusions, we can also construct the power triangle. What will be the value of cos phi? Cos phi is equal to R by Z, or VR by V, which is equal to the power triangle P by S, and this is called as the power factor. Now once we create the power triangle, we know that P is equal to VI cos phi, which is I square R, known as the active power of the RC network, and Q is known as the reactive power of the RC network, which is I square XC. This is not XL, it should be XC. Please make a correction over here, it should be I square XC. And then apparent power, which is equal to I square Z. So we know how to come with one conclusion. For RC network, the current leads voltage by 90 degrees. So this is how RC in series with AC supply is different from RL in series with AC supply. So that is what we have made with the conclusion. I hope you like my video. Please share among your friends, and please subscribe to my channel, and please press the bell icon for future notifications. Thank you.